Point of departure, the Andromeda Galaxy, 2.25 million light-years distant. Destination, planet Earth. Between the Andromeda Galaxy and the Milky Way system, there is nothing. No stars, no planets, no gas. The Milky Way, our galaxy, slowly swims into view. Each of its 200 billion stars is an incandescent ball of hot gas. Past the Large Magellanic Cloud, recently one of its billions of stars went supernova in a blaze of radioactive cobalt and nickel. The dazzling star Canopus, 200,000 times brighter than our Sun, now lies to the left. It has a magnetic field 1,000 times stronger than the Earth's. Now passing Betelgeuse, a cool red giant star that could swallow 400 million suns. 4.3 light-years out, past the closest star to the solar system, Alpha Centauri. And that's the Sun dead ahead. Final destination, planet Earth, and the Anglo-Australian Telescope near Coonabarabran, Australia. That voyage was, of course, pure science fiction, but the facts were real. Take the star catalogue, for instance. It contains the vital statistics of something like 45,000 stars. Things like their temperature, their brightness, even what they're made of. So how can astronomers know so much about things which are just little specks up in the sky? They can't put a star in a laboratory and do experiments on it. In fact, you have to take just what's on offer, and that's starlight. And light detectives seek out the secret codes and messages that are hidden inside. To read those messages loud and clear, you need to gather as much light as possible. And that's why astronomers today build huge telescopes like this, the Anglo-Australian Telescope in Siding Spring in New South Wales. At the heart of this telescope is one of the biggest and most accurate mirrors in the world. This is the telescope's light catcher, by far and away its most important part. The starlight strikes the massive 16-ton curved mirror at the base of the cradle. It's reflected back up to a secondary mirror, which focuses the light to a point behind the main mirror, where it can be photographed or analyzed. If you're going to build a telescope with a mirror that's 3.9 meters across, you don't cut corners on any of the other equipment. Make no mistake, today's telescopes are massive pieces of precision engineering, absolutely crammed with state-of-the-art electronics. This one, for instance, cost $16 million to build back in 1974. Let me show you what it can do and to show you how sensitive it is. This is a part of the sky photographed with an ordinary camera. The blob in the middle, just there, is the Orion Nebula, which is a great cloud of gas and dust in space. Now, here's the same part of the sky photographed with the Anglo-Australian Telescope. And the difference is rather obvious. The one by the Anglo-Australian Telescope just shows the nebula alone, and the detail is absolutely incredible. And that's one reason why British astronomers have abandoned their rather cloudy homeland for sites like this one in New South Wales, which is one of the best in the whole world. Most observatories are situated on remote mountain tops, far from civilization, bright lights, and atmospheric pollution. And here, in the Warrumbungle Mountains at the edge of the Great Australian Desert, conditions are nearly perfect. There are no big cities near the observatory, and the air is quite dry, making for night skies that are crystal clear. The Anglo-Australian Telescope is one of the world's greatest telescopes. Its giant mirror is mounted inside a mobile 280-ton cradle, approximately the same weight as 3 railway engines. As the Earth rotates on its axis and the stars glide across the night sky, this giant computer-controlled telescope can be made to move fractions of a millimeter to track those tiny pinpoints of light. Every telescope is an individual and built to its own specifications. And Peter Gillingham, who knows more than anybody about the ins and outs of the Anglo-Australian telescope, was the engineer who supervised its construction.
The Anglo-Australian telescope has quite a good reputation as being one of the very best telescopes in the world. There are really only 2 or, if you like, 3 telescopes that are significantly bigger. But the AAT has a very good reputation for the precision of the mounting, the efficiency of its use, and in fact its pointing accuracy, the way we can point it to any part of the sky with more precision than at least telescopes up to the time this telescope was completed.
The curved mirror is the heart of the whole system. It's rather like a giant magnifying glass, its surface polished to near perfection.
The surface is accurate to somewhat better than a wavelength of light, peak to peak, that is from hill to valley. And if you, maybe it helps to visualize that by imagining it expanded to a much larger diameter, let's say 8 kilometres diameter, 8 kilometres or about 5 miles diameter. If you expanded it that much, then the surface errors would be about 1 millimetre peak to peak. So it's an extraordinarily accurate surface, so that it focuses light to a very small image.
I've come down here, beneath the mirror, to the place where the starlight is collected. Professional astronomers haven't looked through telescopes for years now. After all, you can't record what you see, and you can't actually see it except fleetingly. Somehow, you have to store and preserve what the telescope takes in, and the simplest way to do that is with a camera. Today's astronomers use cameras like television cameras, like this camera just here. This camera can record stars that are something like 16 million times fainter than the ones you see with your unaided eye. That's as faint as a candle on the moon. Taking photographs with a large telescope totally transforms our impressions of the heavens. With long enough exposures, we can see colors and objects invisible to our insensitive eyes. Pictures like this are the first step in gathering all the different bits of information we need to find out what stars are. That stunning photograph was taken with the Anglo-Australian telescope by one of the world's greatest astrophotographers, David Malin.
It's a fantastic feeling sitting there at night, taking photographs of the sky with the stars behind. I mean, you can turn around and look at the night sky and the stars are sparkling there. But also I like to get them in the laboratory and extract photographs from them. When you fish the plate out of the fixer, you're looking at something that nobody's seen before, because the eye isn't sensitive enough to see any of this. Even when you look through this telescope, which is a very unusual thing to do, but occasionally have a quick glance, you don't see these objects at all, often just a faint wisp of grey filaments. But when you get in the darkroom and fish the plate out of the fixer, it's covered in nebulosity and stars and things of interest, and you know you have a winning picture.
David Malin's pictures tell us only part of the story. To find out more about the messages hidden in starlight, many astronomers need to adopt a more high-tech approach. Here's the same part of the sky, the Orion Nebula, captured with a more sensitive electronic camera called a charged couple device. It's registering infrared or heat radiation from young hot stars.
The business is being taken over by electronic detectors. And they have all kinds of advantages. For instance, their data is digital and they can talk directly to computers. But they're only limited to a tiny part of the sky, about the size of a postage stamp, whereas my plates are 10 inches square. And so I can look at wide angles of sky. Although their plates are much less sensitive than the charged coupled device, they give you a much bigger patch of sky to play with.
Today, astronomers can examine starlight and work out how hot, how far away, and how big stars are, and even what they're made of. The first message from starlight can be read from photographs like these. They reveal the true colors of the stars. But what causes these different colors?
Well, I've always wanted to get my hands on one of these things, so here's my chance. Everybody knows that a cold substance, like this metal bar here, doesn't give out any light. But if I apply heat to it, it should begin to glow. So let's see if it all works. It's beginning to give out a red glow. That's the first stage. Now let's see what happens if I heat it a bit further. Off we go again. Now, as you can see, the glow is distinctly orange, and it's getting quite a bit brighter. So let's carry on heating it and see how far we can take it. Now it's yellow, and as I keep up the heat, gradually, the center of this is beginning to turn white. Now, if I kept up the heat indefinitely, it wouldn't just glow white, it would start to glow bluish white.
This sequence of increasing hotness is as true for the stars, which are made of hot gas, as it is for the iron bar. And you can see these colors in the stars with the naked eye. For instance, the star Betelgeuse in Orion is red. It's a cool star with a temperature of only about 3,000 degrees Celsius. Arcturus in Boötes is orange, a little bit warmer at around 4,500 degrees. And the star Capella, like the Sun, is yellow, both with temperatures of 6,000 degrees. Sirius, the brightest star in the sky, is white, revealing a temperature of 10,000 degrees. Amongst the hottest stars of all are those like Spica in the constellation of Virgo. Its blue-white color puts its temperature at 20,000 degrees. And there are some fairly rare stars that are hotter still, with temperatures over 100,000 degrees. Another message hidden in starlight is a star's brightness, which tells us how quickly it is burning its nuclear fuel. You can measure very accurately how bright any star seems to be, but first you have to find out how far away it is. When you look at these two stars in the Plough, for instance, they look the same brightness. But are they?
Without knowing how far away each one of those stars is, you've absolutely no way of knowing. For all you know, one of them could be a real cosmic searchlight at a tremendous distance, while the other might be a little glowworm right on your doorstep. It's a classic case of the torch and the motorbike light. As you see, the torch is really very, very dim, whereas as Tom draws closer to me, his motorbike light is literally hundreds of times brighter than my little torch just here. It's just the same out in space when you've got two stars that might look the same, but in fact one might be hundreds of light years away and literally thousands of times brighter than another one. So how do you measure the distances to the stars? The answer is with great difficulty. That's why nobody succeeded in doing it until midway through the last century. At least the idea behind it is straightforward enough. It relies on the fact that when you look at a nearby object from two different vantage points, it appears to shift against a distant background. To give you an idea of what I mean, let's kill those lights and imagine that my torch here is a nearby star. The lights you see in the background behind me are those of a distant town. They're like the distant stars you see in the sky. Now, I'm going to stay completely still, but what you're going to see is my torch, our nearby star, viewed from two different vantage points as the camera begins to swing from one position and then to another position. And as the camera moves, you can see the star is moving against a background of more distant stars which are completely fixed. This is the principle behind which astronomers measure distances to the stars, except that their swinging vantage point is the shifting of the Earth as it moves around the Sun, around the Earth's orbit. But even with an orbit as large as the Earth's, it measures 186 million miles from one extreme to the other. The shift of even the nearest stars is so small that it needs the largest telescopes in the world to be able to pick it up at all.
Using this technique,
astronomers can find out that even the closest star to our solar system, the triple star system Alpha Centauri, is 25 million miles away. And you'll be pleased to hear that astronomers are no better at coping with these large numbers than anybody else. So they've invented a kind of shorthand to describe them. They measure the distances to the stars not in miles or kilometers, but by how long it takes their light to reach us. But first, you have to know how fast light travels. In the 1920s, the physicist Albert Michelson managed to measure the speed of light with great precision on Mount Wilson above Los Angeles. He bounced a beam of light off another mountain 22 miles away and compared its round-trip journey time with the speed of rotation of a mirror. He found that light travels at 186,000 miles per second, the speed limit of the universe. It took less than 1,000th of a second for Michelson's flash of light to make the 44-mile round trip. Light takes just 1 1/4 seconds to reach us from the moon, 250,000 miles away. From the sun, our nearest star, it takes 8.3 minutes. And so we see the sun not as it is now, but as it was over 8 minutes ago. Jupiter is over 30 light minutes away, and the edge of our solar system is over 5 light hours away. But these distances within our solar system are nothing compared to the distances to the stars. Light from even the Alpha Centauri star system takes 4 years to reach us. But at least it's easier to say that it lies 4 light years away, rather than 25 million miles. A light year is a distance, 6 million miles, the distance light travels in a year. Many stars are hundreds or even thousands of light years away. And the most remote object visible without a telescope, a star city way beyond the Milky Way, called the Andromeda Galaxy, lies 2.25 million light years away. At these astounding distances, stars appear only as pinpoints of light. Even the closest stars are just dots. On this picture, the brighter stars look bigger, but that's no indication of their true size. It's just a photographic effect. No telescope on Earth will show a star as anything but a point of light. So how can we measure how big a star really is? The answer is with a spot of lateral thinking. Inside this anonymous shed in Sydney is an incredibly sensitive device. It's called an interferometer, and it really does work laterally. It detects light beams from opposite sides of a large star. These beams interact with each other in a way that reveals how wide the star really is. This deceptively simple apparatus is the brainchild of astronomers John Davies and Hanbury Brown.
In a big telescope, for example, you could look at a star, and if the telescope was big enough, you could get an image of the star which would actually show its angular size. But you need too large a telescope to do that. To measure some star like Sirius, for example, you'd need a telescope something like about 30 feet across, at least. And of course, you can't do that. So instead of building one huge glass mirror, you take 2 small pieces of glass, space them apart, and you compare the light which is received on these 2 small pieces of glass, which avoids having to build a big telescope.
With their interferometer, Hanbury Brown and John Davies have measured stars from 3 times to hundreds of times bigger than our sun. They have found that some stars are so huge they would swallow up our entire solar system.
A very large fraction of matter is in the form of stars in the universe. And in order to get an understanding of stars, what they are, how they're actually structured, and how they evolve with time, we need to make measurements of their physical size, of the masses involved, of the total energy output, because this is linked with the nuclear processes that are going on inside. And the sort of measurements that we propose making, measuring the size, is actually the angular size is what we measure. When you link this with measurements made with conventional telescopes, measurements of the amount of energy received, the speeds of rotation and so on. When you link these different pieces of information together, you do in fact get the physical size, you get the masses of stars, you get the total, you get the surface temperatures, you get the total energy output.
Starlight tells us an enormous amount. How hot a star is, how far away it is, how bright it is, even how big it is. And now we are even able to know what a star is made of. For hidden deep in starlight itself is the ultimate message for astronomers, a star's spectrum.
And a spectrum is a pattern of light. Hidden in this pattern are the clues to a star's makeup, because each wavelength in the spectrum is a signature from a particular gas within the star. Just as a musician would recognize the notes making up the chord of, say, C major, so I, or any other astronomer, can tell by looking at this spectrum here that the star contains nitrogen, helium, and down here, oxygen. In fact, each star's spectrum is as individual as a fingerprint. This particular spectrum is the end result of grabbing the star's light with a telescope, spreading it out with a spectrograph, channeling it through a computer, and finally feeding it to this TV monitor here in the telescope's control room. This is where, in warmth and comfort, an astronomer can watch the build-up of any star's spectrum as the data from the telescope starts to pour in during the night.
But all this is just the beginning. For every night an astronomer like Max Pettini spends at the telescope, he'll spend at least a month in the office, analysing the observations he has so carefully stored on computer disk. His two spectra here reveal how stars have changed since the birth of the universe.
And the spectrum at the bottom is the same part of the spectrum, but now in an old star, and what we call a white dwarf. And there is a great deal of information that astronomers can deduce by comparing these two spectra. For instance, the normal young star at the top, as you can see, shows a variety of absorption lines. And each of these absorption lines, in fact, occurs at a very precise wavelength. And it is that wavelength that allows us to identify it as a signature of particular elements. The strongest feature is a line of hydrogen. In the old white dwarf star, which is at the end of its evolution and its lifetime, we can see very little other than the hydrogen line. And the reason for this is that when the old star formed a long, long time ago, hydrogen was pretty much all there was about in the galaxy for the star to form out of. And it's only subsequently to that, only in later times, that the elements from which we are made, like iron and titanium, were in fact manufactured in the galaxy.
Max Pettini's work on the chemistry of stars confirms the pattern that has been emerging. Like our sun, every star is an individual, each with its own character. Amongst these thousands of stars, there are thousands of different personalities. An astronomer's job is to make sense of all this bewildering variety.
But the stars aren't as fundamentally different as it seems. They just change as they go through their lives. And we've been able to find that stars have lives, very long ones, from the message hidden in starlight. In fact, looking at stars is a bit like being in a wood of trees. An alien visiting this forest would see all kinds of trees, big trees, small trees, and trees that had fallen down. Without too much thinking about it, he'd be able to work out that what he was seeing was different stages in the life of one particular kind of tree. And so, without ever seeing a tree grow, he could work out a tree's life cycle. This is no esoteric message for astronomers alone. By interpreting the message from the distant stars, we can understand more about our own star, the sun, the star that our lives depend upon. today have got one of these little gadgets, a solar-powered calculator, which relies for its